Okay, so in this second numerical example, which is 3174, and which is again taken from the Gen Merriam book, and is one of the numerical example in your tutorial sheet. So as you can see in this figure here, that 1500 kilogram car has a velocity of 10 kilometer per hour up the 10% grade when the driver apply more power for 8 seconds to bring the car up to a speed of 60 kilometer per hour, and calculate the time average force of the total force tangent to the road exerted on the tires during the 8 second, and treat the car as particle and neglect the air resistance. Okay, so again in this case, as you can see, that you need to calculate the force which change the velocity from 30 kilometer per hour to 60 kilometer per hour, and the force is applied for 8 seconds. So again, for this problem it will be straightforward to use the equation of impulse and momentum, because you are given the velocities and you want to calculate the force. So to avoid the calculation of acceleration, you just need to apply the principle of impulse and momentum here. But before trying to solve this question, it's good idea to draw the free body diagram, so you know all the forces which is acting on this car here. Okay, so as you know that let's just is okay. So the first thing is you are given the v1, which is the initial velocity of the car, and which is given is 30 kilometer per hour. So it's always good idea to convert the velocities to meter per seconds. So it will become 30 will become 8.33 meter per second, and then v2 is again is 60 kilometer per hour, which is given, and this will become 16.67 meter per second. Okay, and again you are given this this angle here. So if you go 10 units on the along the in the x direction, you are going 1 unit in the y direction. So this is the slope of this road which is given here. So this means that from here we can calculate the angle here. So if you want to calculate this angle theta, for example, so this theta will just become tangent inverse 1 divided by 10, and this will become something like 5.71 degrees. You can calculate the actual angle associated with this road here. And now we need to solve this problem, but we need to identify all the forces which is acting on this case here. And again you are given the mass of the of the car, which is 1500 kilogram. So you can take the car on this inclined road, and this angle here is given, which is 5.71 degrees here. And okay, so the initial velocity, which was somewhere here, is 8.33, and the final velocity, which is going to be here, which is 16.67 meter per second and meter per second. Now, so the thing is, we need to now identify all the forces which will act on this car. So first is the driving force, which is changing the velocity from 8.33 to 16.67, and that will be the applied force, and which will be in this direction here. So that is the applied force F. That is what we want to calculate. And again, because the body is moving on inclined road, so its mass or its weight will be opposing its motion. So we also now need to include that in the calculation, because we cannot ignore the weight here. So the weight of the car will be mg. So m is given, which is 1500, and g is 9.81. So now we can split this mg into two components. So one will be normal to the plane, and one will be in the direction of the plane here, or in the direction of the road. And this angle is theta here. So because now this mg is perpendicular to this horizontal, and this is the road, and then now this one is perpendicular to the road, this means that this angle is also theta here. So this means that this component become mg sine theta, and this component, which is adjacent side, will become mg cos theta. So now we have all the forces. We have identified all the forces on this car. We can also now identify the maybe the x and y direction of the motion here. We are assuming that our x is in this direction here, y is in this direction here, because the body is moving only in the x direction. So it will be easy to just consider x in this direction, so that we avoid the calculation in the y direction. So if you consider this figure here now, and now we know that the equation of impulse and momentum. So the impulse and momentum equation is g1 and plus t1 to t2 summation of all the forces into dt equal to g2. So this is the impulse and momentum equation here. But we can also now write this in graphical form, so that we identify all the known and unknown in our calculation. So as you can see here, what we will have. So if you consider this is our x direction now, and this is the y direction now. So the g1 is in this direction, which is mv1x, and then you have, so again, this is our car, which we are assuming is particle, and then you have all the forces which is acting on the particle or on the car in the x direction. So one is the applied force, which the driver need to exert on the car to change its speed from v1 to v2. So which is in the positive direction, because we want to increase the speed here, so which should be in the positive direction. And the time is given. So the time is given, which is 8 seconds here. So the time here will be from 0 to 8, and this will be f dt. And then this component of the weight, which is in the negative x direction, we should also write this component here. So this will be from 0 to 8 mg sine theta dt, because this weight is also acting on the car for that specific time. So the weight is also acting from 0 to 8 seconds here. So therefore we also need to integrate the weight here. And then on the equal to, on the right hand side, we have g2. So g2 here is just the m and then v2x, and obviously we know the v2x here. So this is just the this was the mathematical way to write the impulse momentum equation, and this is the graphical way to write the the impulse momentum equation here. So now we can just write all these equation in the in just a simple equation here. So mv1x, so mass is given, which is 1500, and v1x is given, which is 8.33. And now you have the impulse here, which is the integration of the forces. So in this case, you have this F, which is this F here. So which is this here F. So F is constant force here. And if you integrate this constant force with respect to time, F, so you can take this F outside because it's a constant force. Then you will, in the bracket, it will be just 8 minus 1. And then again, you will have mg sine theta. So m is given, which is, but in this case, because it's in the negative direction, so you will have to subtract this force. So mg, which is 1500, 9.81, and sine up 5.71 degrees. And then obviously you are integrating it with respect to time. So because everything is constant here, so you can take this out of the integration. So it will become just integration of 1, which will become t. And then if you put the limits of integration, it will become 8 minus 0 here. This one is also 8 minus 0 because you just put the limits of the integration and it's become 8 minus 0. And then on the other side, we have m v2x. So m is again given, which is 1500. And v2x is given, which is this, the final velocity, which is 16.67. Now, if you look at this equation here, the only unknown in this equation is just this f here. And it is just a simple simple mathematical equation. So you can just solve this equation, and from here you will calculate f, and which will be 3028 Newton. Or you can convert this into kilonewton, which will, if you just divide this by 1000, so you will get this force here.